Okay, so I'm recording now. Welcome everyone. Let me share the screen with the presentation. Okay, and sorry. Okay, good. Slideshow, yes. Okay, so I hope you have my presentation on the screen. And we'll be talking about mathematical induction, so sections 8.4 and 8.5. What is induction? It's a technique for proving some statements which are parameterized by infinite sequence of integers. Okay, so what? Okay, the best is the example. So here you have a statement that says that some equation is true, namely this one, and this equation is whether or not this statement is true is really a predicate on integer n. So look, the left-hand side of this equation, it's a function of n, right? So for this is a summation. J is just a free variable that goes from 1 to n. So what is this symbol? This is a summation of first n integers, positive integers. It is some quantity that depends on n. So it's a function of n. And so is this side, right? It's a numerical expression that is a quadratic expression in n. And what does this statement say? It says that whatever this function of n is, then on every positive integer argument, this function on n and this function on n have the same values. Okay, and that's a predicate on n. So it's a statement that is parameterized by an argument, where the argument is a natural, is an integer. We know what statements that are parameterized by variables are. They're called predicates. A predicate is essentially some function of some variables that returns true or not. Now, if you think of this as a predicate on n, which says this stuff is a function of n, is equal to this stuff, another function of n, that's a predicate about n. Perhaps it's true, perhaps not. This theorem says that it is. And if you can read off this predicate on n as follows: sum of the first n positive integers, which is this part, equals n squared plus n over 2, which is this, right? If you multiply it as n squared plus n over 2. It's a predicate, and it happens to be true. It's not obvious immediately, right? Like just by staring at this, that it is true, but it is true. Okay. Induction is a very good technique for proving statements like this true about. Now, what do we mean that is parameterized by infinite sequence of integers? Well, because this statement is, the parameter is n, right? It's the argument in the predicate. And how can you prove such a thing true for all n? Well, you can try to somehow prove it from scratch. Somehow manipulate this summation so that in the end of manipulations of the summation, you will have a product of the end and the end plus 1, and moreover divided by 2. But if you look at the summation, it's not going to be so obvious. How do you manipulate? Although you could actually, right? So think of, okay, or leaves you off, like, how would you prove that directly? There's a sort of geometric argument that you can, right? And once I say geometric, maybe you will see it. But induction is also very useful in a simple tool to prove this. And the induction proof goes like this. Let's say that you have some statement that is parameterized by an integer, like this predicate. The predicate we had on the previous slide, that the sum of the first n positive integers is n squared plus n over 2. And say that you're claiming that this predicate holds for all integers greater or equal to 1. Sorry about this. Well, you can prove it by proving the inductive proof of this statement would consist of 2 parts. First, the base case. Look, the first integer for which we have to prove this is n equal 1. Okay, we're going to isolate this as a special case, the sort of the smallest integer for which we want to prove this. So this will be the base case. We'll prove that p of 1 is true. Namely, this predicate holds for n equal 1. That's the base case. The inductive step has the following form. We'll prove for any positive integer, call it k, although you could call it n, and you could call it m, and you could call it j. It really doesn't matter. We call it here k. As long as this integer is greater or equal to 1, then the following implication must hold. The implication is that if this predicate is satisfied at index k, then it also must be satisfied at one more index, k plus 1. You can read of this statement as following implication. What you're proving is that for all k, the following holds. As long as k is greater or equal to 1, like here, and the predicate is true about k, then it must also hold that its predicate is true for k plus 1. Now, this statement and this implication, the implication preceded by the for all, together imply this statement, that for all integers n, Pn holds. It's a sort of a meta statement that you can prove any predicate holding over an infinite range as long as you prove it, this predicate holds for the first element in the range, and secondly, prove the following implication, that if an integer stands for any integer in the range, that if it holds predicate on that integer, then it holds at the next. These two statements together basically unroll into proving the statement correct for all integers, positive in this case, right, in this range. Why is that? Okay, so look, so base case obviously implies that P1 is true. It is the base case verbatim, right? But look, if you instantiate, inductive steps shows that for any k, this implication holds. Any k at least 1. So let's instantiate this implication with for first case, k equal 1. What does this implication say for such k? It says that P1 implies P2. It says this. And you know that both this is true by base case, and also this is true because it's an instantiation of this general implication. General meaning because it holds, you show that true for all k. For just specific case of k equal 1. And now that you have these two implications, it must follow that P2 is true. Because if, this is in the form of P implies Q, and P is true, therefore Q must be true, right? Or otherwise this implication will not hold. You cannot be that the beginning of the precedent in the implication is true, but antecedent is not. So it must hold. So you can conclude that P2 is true. And then you just recurse. Sorry, so okay. Instantiate the inductive step for the next integer, k equal 2. So for that integer, the inductive step says P2 implies P3, but you already established that P2 is true. And therefore, repeating the same motion, this implication couldn't hold unless the subsequent also held, right? Because otherwise you would violate the supposed implication that P2 implies P3. So the only word in which agrees with the fact that P2 is true and this implication is true is the word in which P3 is true. And so on. You apply the same procedure, right? Which in order to prove the statement true for any integer, you can, by just doing this, whatever that integer is that many times, right? So if you want to prove it for 10,000, this proof will be 10,000, we'll have 10,000 steps. So it's a little philosophical thing, like what does it mean exactly that you're proving it for all n? Well, because for any n, this proof exists. It's just an instantiation of this rule in a loop. For increment, you increment the counter, and you just write out these rules, and all of this is implied, right? It is kind of similar to just as recursive definitions, recurrence relations, defining a sequence, next element of the sequence in terms of the previous. It's like a recursive programming. You define the value of the function at some argument in terms of the value of the function at the previous argument. Here, you can read of this as a way to define truthfulness of this predicate as a function of whether or not P is true about the previous integer. So this implication is kind of a recursive call. If you want to evaluate, let's say you want to evaluate, is P true at 1000? Well, you instantiate this rule for k equal 999. And you say, well, P of 1000 would hold if P of 999 held. All right, so let's check, let's do a recursive call. Let's check whether P of 999 holds. Well, it would if P of 998 held. And you do it 1000 times, no problem, because you're an algorithm, and you hit the base case, which is true, which now implies through a series of evaluations that it is true about k, for n equal 1000, right? So it is another recursion in disguise, but now the recursion that allows us to evaluate truthfulness of predicates at some instances in terms of their truthfulness at previous instances. So if you squint your eyes, it's a recursion again, and basically programming again. All right. So, by the way, you can, if you want, you ask questions. Like you just have to unmute yourself, and I will. Sorry, I'm taking a break so that to switch on my chat window, which somehow evaporated. And I do not know how to do it. So, okay, so I will not have a chat window open during this this lecture, but all the more, just unmute and ask a question if there's something unclear. Okay.
There are also different kinds of inductions, like there's a strong and like other.
Yeah, next Thursday. That's Thursday. True. True. Just wait till Thursday. Yeah. Or of course read about it. All right. Okay. So let's see it for some case. Right. So we have this predicate that we started with. It's a predicate that says that the sum of the first n integers, positive integers, is equal to, sorry, n times n plus 1 over 2. Okay. Let me, I pray this will work. Okay. Now, do you see a, hold on, show grid, show thumbnail. No, hold on. Document camera, Alt N to switch. It worked. Okay, I have to do stop sharing. I see. Hold on a second. Just hold on a second. I want to switch to okay. So I guess I have to do this to get to exit the document view. And now switch to the different camera. Yes. Okay. Okay, just wait a second. It will come into view. Okay, good. So, here we had this predicate, right? That the sum of first n integers is equal to n squared plus 1 plus n over 2. And we claim this is true for all integers, positive integers. Okay. Oh, I see your chat messages, so now you can also say something there if you want. I mean, to me. Inductive proof. All right. First, the base case. So in other words, we have to argue that this predicate is true at the first index, which is this one, right? N equal 1. All right. So let's show that P1 holds. Now, what is P1? It's a little hard to read at first. It is a statement that this predicate holds when instantiated when n equal 1. All right. What does this say for n equal 1? It says something sort of super simple, so it might not be immediate to see. That's the only difficulty in the base case. So what is this summation for n equal 1? So you're summing from j1 to just 1 and over j. So this whole summation is just 1, right? Because this is the sum. What is the sum of the first 1 positive integers? It's just 1. So this summation is just 1. What about the right-hand side? Well, it's a quadratic formula on n. So let's just instantiate it with n equal 1. Well, so it's 1 plus 2 times 2 over 2, that's 1. So both the left-hand side and the right-hand side of this equation for n equal 1 are equal because they're both equal, happen to be equal to the numerical value 1, right? This is not important. What's important is that they're equal, okay? I mean, it is important, but not really now. What you're showing now is that this is equal to that, and it is. All right. So let's move on to the inductive step. What in the inductive step, you have to show that for any k, if, what is this? This is P of k. This is a predicate that says that this statement is true at integer k. And what is the statement at integer k? Well, that the summation of first k integers is equal to k times k plus 1 over 2. And if this statement is true about k, then we have to show that it's also true about k plus 1. So now you can see that this inductive step basically had a form for every k greater or equal to 1, show that if predicate holds on k, then it holds on k plus 1, right? That's the form, that's the universal form of the inductive step, and it is here. It is just enveloped for the particular predicate P that you want to prove. All right. So this is what you have to prove in the inductive step. In other words, you have to prove that if it is the case that this closed formula, so what are we claiming here, right? We have a recursive formula, right? Because what is the arithmetic? What is the summation? It's a sum of an arithmetic series, right? It's a series that is the simplest arithmetic series, 1, 2, 3, 4, 5, 6, and you're summing. Okay, so as you know, arithmetic sequences or geometric sequences are basically recursive sequences, right? The first guy is 1, and the rest of the sequence is defined as the next one is 1 plus previous one. So you have basically here something like a recursively defined sum, and you have a closed formula for it on the right, right? So rather than evaluate it using this recursive formula, you now have a closed form expression for it. This predicate claims that this recursively defined thing is equal to this closed form expression. All right, so coming back, what you have to do in the inductive step. So in the inductive step, you're proving that if it is the case that the sum of the first k integers is expressed correctly by this closed formula, then it is also the case that the sum of k plus 1 first positive integers is likewise expressed correctly by the same formula. Of course, this formula now is instantiated with n equal k plus 1, right? But it is the same formula. This is the formula for n equal k, and this is the formula for n equal k plus 1. right? So in other words, in the inductive proof, if you are, instead of showing by scratch somehow that this recursively defined object can be is equal to this closed form expression, instead what you're making your job easier by saying, if at some point, okay, this is closed form is correct, and you don't kind of know, and you don't really rely on it that it is correct, you're like saying if it is correct, then the same formula would hold for the recursive object defined at one extra point. Okay, and now why is this really a boon for us, right? Because look, this is my goal. I want to say that this sequence summation is equal to this closed form formula. But in this proof that this is true, I can use this assumption, because all I'm proving is an implication. If this assumption holds, then I don't know whether it's true or not. I don't have to prove whether or not this is true. If it is, then I have to prove this. And that makes my job easier. So let's see, I'm trying to prove this statement, assuming this is true. How could I do this? Well, this is a recursive object that really has a very easy relation to this one. What is the recursive definition of the arithmetic formula, of the summation? This sum is just this one plus the last element. In other words, I can rewrite this summation as the summation from j to k, right, plus the last element. And what is the last element? It's the j equal to k plus 1. This is the last element. So right here, you have basically recursive definition of summation of arithmetic series. Okay. Yeah, well, actually, it's just any summation of summation, right? Okay. So, and now you're basically almost home, okay? Once you did this rewrite, because now you can say, aha, I'm supposed to assume, I am allowed to assume that this formula, closed form expression, was correct for summation up to one less element, which is this one. So at that point, here, use the inductive assumption. Use the inductive assumption, namely, use this thing. Okay. To rewrite this as k times k plus 1 over 2, right? Because we're supposed to be able to assume that the closed form has at one less index.
Oh, just would you mind to move up a bit? Oh, thank you.
Yes. So there is a bar of this thing, and I just realized it's the first time that the bar makes it harder. But thank you. Right. Okay, so, and I rewrite this term, right? Because this term is just a rewrite. The rest is just arithmetics. I have to somehow get from here to here, because that's what I'm proving, right? That this thing is equal to this. So I need to get to here. But now I have I already have a closed form formula. So I just need to check whether this formula is really equal to that one. Well, that's not hard, right? Because this is, I just have to make them, okay, say like this, right? Like I just put this up, multiplied by 2, and now you can see that this is k plus 2 multiplied by k plus 1 over 2, right? So I just represented k plus 1 as 2 k plus 1 divided by 2, right? And at which point I could add these two fractions. And that is the, so look, my walk was, I started from the left-hand side of p k plus 1, and I ended with the right-hand side of p k plus 1, and therefore I have proved that p k plus 1 holds, because the statement p k plus 1 was that the left-hand side is equal to right-hand side. And I made two crucial points. The 2 points are this one and this one. So step 1, relate something about pk plus 1 to something about pk. And in our case, it was the left-hand side. The left-hand side of pk plus 1 has an easy recursive relation to the left-hand side of pk, and that's this relation. Because this is a really recursively defined object. This object is defined as a simple formula in terms of this one. Namely, this is the formula. Okay. Step 2, kick in the inductive assumption. Right. Now that you have rewritten something about the statement in terms of this one, now you can kick in the inductive formula to rewrite this as that. And this is the trivial rewrites after that, right? So I'm not using really anything. I'm just using. Oh, sorry about. I kept it down. Right. This is just arithmetics, which might be challenging sometimes. Might actually, the hardness might be in here in these changes. Okay. So questions, or I will just go to the next one. And I will, I will upload these sheets of paper for better or worse. Somebody is complaining that the writing is not that great. Yeah, well, I guess it's a speed versus clarity, but right-hand side means.
I have a quick question, Professor.
This is right-hand side of the expression, right? So the expression is inequality, and it has left-hand side and the right-hand side. So that's what I meant by.
Wait, Professor, I have a quick question.
Mm-hmm.
So how come you simplified k times k plus 1 plus 2k plus 1 2 times k plus 1 into only k plus 2 and k plus 9? Like, how did you get from there to there?
Well, yeah, so I replaced this by that.
Okay, but then when you add them together, it shouldn't be. Then why is it equating to k plus 2 times k plus 1?
Oh, this one? Well, because you have something times k plus 1 plus something times k plus 1. So you can take k plus 1 out and then just read off what are these somethings. This was k and this was 2. They're here.
Oh, right. You factor them, right? I see. Yeah.
Yes. Well, because I know my goal. I know that I want to show this equality with this. So that's where I want to go, right? So I just, you can express this thing in many, many different ways, but I want to express it in this way. So I know where I'm driving towards, right? I have to express this as some factor involving k plus 1. So that's what I did. Okay, let's, oh, I can make it larger at the, but then it will be smaller as well, it's larger and smaller. All right. Okay, let me go back to the presentation. Okay, that's the example we just had. Okay, so again, the predicate said this, and what we were, sorry, right, and it was convenient to express the predicate as equality of two functions, the left-hand side function and the right-hand side. Both of them are functions of n, and the base case just showed that these two functions have the same value at argument 1. And what did we show in the inductive case, right? what we showed in the inductive step was a form of implication. If this formula held for some k, for essentially with the k, if the predicate held for some k, then it held for k plus 1. I don't see your chats, unfortunately, so I cannot tell how you're voting, but this is the one, because this is the predicate essentially p essentially with k, and this is the predicate p essentially with k plus 1, and that's the one we were proving on paper. All right, so let's look at another inequality. Okay, so another example. You have you claiming that n factorial is greater than n square, and that this holds for all integers greater or equal to 4. There's two differences. We don't start at n equal 1 or 0, or it was 1 last time, right? We start at 4. Okay, but and that doesn't really change anything fundamentally, right? We're proving stuff for all integers starting at some point. The other change is that you're not proving equality of two expressions, but inequality, that this expression is always greater. Okay, let me go to the okay, to try to do this on paper. So here is my predicate. It says that n factorial is greater. Sorry, it was a strict inequality. It says that n factorial is strictly greater than n square. Okay, and the claim is that this predicate holds for all integers at larger or equal to 4. Proved by induction. What is the base case? Well, we have to start at the beginning of this infinite sequence of integers. So the base case is that Pn holds for n equal 4. In other words, that P4 is true. Now, what does P4 say? P4 says that 4 factorial is greater than 4 square. What is 4 factorial? That's 1 times 2 times 3 times 4, right? So factorial, n factorial is the product of all consecutive integers, right? We just looked at the sum of consecutive integers in the previous example, and now we are looking at product of consecutive integers. Why are we doing these? Because they have easy recursive interpretations. They are sort of in an obvious way defined recursively in terms of the same formula at smaller index. So what is this? So this 2 times 3 times 4 is 6 times 4, right? So that's 24. And what is 4 squared? That's 16. Okay, well, it is true that 24 is greater than 16. Check, right? You have basically just convinced yourself that and others that P4 holds because this statement is true. All right, what do you have to prove in the inductive case? So again, inductive case is that for all k indices, and where do we have to start? Well, the starting point, which is 4 in this case. If the predicate holds at k, then it has to hold for k one more. Okay, now for this particular case of the predicate, right, which this predicate, let's write what this formula says. It says that we have to show that for every k greater or equal to 4, if k factorial is larger than k square, then k plus 1 factorial is greater than k plus 1 square. right? Because this is the predicate pk, and this is the predicate p at point k plus 1. That's what these two predicates say, right? So let's use the same basically methodology, okay, which is the same approach. This is our goal. We have to prove this, but we can use this within the proof. Well, how do you relate anything here to anything here? It's this side that is in an easy relation, because as product of consecutive integers up to k plus 1 has a sort of an easy relation to the product of all consecutive integers that stopped at k. And what is this relation? Well, k plus 1 factorial, the left-hand side of this expression, is k factorial times the last one, right? So this is what I'm using. Here I have the left-hand side of the predicate of this predicate. Now, not all predicates are formed in terms of some formula with some arithmetic relation to some other. Okay, so it is not always true that there is a left-hand side and right-hand side. There is more complicated predicates. But now I have the case of such. Okay, relationship of well can be related to the left-hand side of pk. And what is this relation? This is the relation. It is the recurrence relation of product of consecutive integers, right? It is because these two objects are really, factorial is a recursively defined object. A factorial at k plus 1 is the factorial at k times k plus 1. Okay, that's how you could evaluate factorials. Okay, and now that you've done this, so okay, good. So now, hey, fantastic, because we can assume this hypothesis, this assumption. So we can now say, okay, k square is we are supposed to be able to use that k square is greater than that k factorial is greater than k square. In other words, we can confidently write that this expression is greater than k square times k plus 1. Right, so what did we use here? Used the inductive hypothesis, right? In other words, this thing, right? We just kicked in here. Because we are not proving this directly, we are proving this if this held. So let's assume this held and see what happens, and whether in particular this is going to imply this predicate. Okay, now I have those arithmetic expressions. So what can I do with them? Okay, what is my goal? My goal is somehow to show that whatever this is at least k plus 1 square. If I could show that this is at least that, then I would be done, because I would be showing that this is at least this, right? It's strictly bounded below by this. Okay, so let's look. Okay, so well, this I can see. Okay, this is the k plus 1 times k plus 1, and this is something times k plus 1, and this is something times k plus 1. So if I can show that k square is greater than k plus 1, then I will be done, right? Because this thing would have to be greater than this thing then. Well, so my sort of, is k square greater or equal to k plus 1 for, and it doesn't have to be true for all integers, it just have to be true for k greater or equal to 4. Okay, Well, and it's sort of obviously true, right? So, I mean, you can show this in many ways. You know, one of them is to show that 1 minus chi minus y is greater or equal to 0. This is a quadratic equation. But if you basically tell us that this is just a true thing for k greater or equal to 4, it's fine also, right? So you don't have to solve this quadratic expression to show this. Although you could. So you can say that this is at least k plus 1 times k plus 1, which is equal to k plus 1 square. Okay, and here you use this. Okay. Okay. Why aren't we showing some sort of why are we showing this funny relation? Why not a closed formula? Well, a closed formula for factorial is not known actually. I mean, there is some bounds for factorial that you can show nice bounds, but there is no there is no closed formula. There's just bounds. It will actually be true also that the factorial is bounded above by n cube if you hike up the beginning n, and it's also n to the 4th. So in fact, factorial is bounded by below by any polynomial if you start high enough. So this function is growing faster than any polynomial, but we're just showing the simple thing that is faster than a square. Okay, let me go back to my slides. Okay. Okay, so here this. Okay, so I actually have this written out on the PowerPoint as well. So I'll just run through it. Oh no. Oh, I forgot that I have this animation here. That's kind of annoying. All right, especially since I've done it on the piece of paper. So again, in order to prove this, we first just found this. If you forget this relation, the recursive relation, then just write out what this is, right? Which is here, and there's notice that this part is the case factorial. So you can rewrite it this way. Now kick in the inductive hypothesis, right? Namely this one at this step, and keep on rewriting stuff. And here is the direct proof that this holds. Okay, so it just happens to be. Here is one way you can directly relate the k square to k plus 1. Replace k squared by k times k. Replace bound k above by 2, which you can because it's bounded from below by 4, right? So it's k is at least 2 as well. At this point, you can replace 2k by k plus k, and at this point you can also replace k by bound k from below by 1, right? K is greater or equal to 1 because it's greater or equal to 4. So these are the direct steps you could use. The whole point here is to show that k squared is at least k plus 1, which is sort of an obvious thing that you can show in many ways. Okay.
Could you explain how you got from step 4 to step 5? Like, how'd you sub in the 2?
Well, you see, okay, I did it so that it fits. I did it so that to show that k squared is at least k plus 1. That's all I have to do. And it's sort of an obvious thing that k squared is at least k plus 1. But okay, even though it's obvious, it's like, how do you exactly show it? Well, there is many ways to do so. here's just one series of rewrites that allows you to do so, right? If you just note that k times k is at least k times 2 if k is at least 2. That's all that's happened here, right? K is at least 2. That's why you can put this sign between this expression and this expression, because k is greater or equal to 2. Therefore, k times something positive must be greater or equal than 2 times the same thing, right? And this stuff is positive, right? So that's why this inequality holds. And once you've done that, then this is just another funny rewrite, right? Instead of 2k, I write k plus k, and I say that k plus k must be at least k plus 1, because k is at least 1, because that follows from here. All right. So you can be like, how did I come up with these? I just came up with it so that it fits. But if you ask, like, why is this true? Well, it's true. It's sort of elementary. These are just elementary transformations. Okay. Oh, somebody asked, is k times k equal to k squared? Yes. All right. Okay. So here's another statement, and you can prove by example of another statement provable by induction. The statement says that for every integer, let me just say one thing, that like this is not the easiest case you can have of induction. So this is just this step is like to argue that this is larger than that is not immediate, and it's not like that you are supposed to be able to come up with these steps like in a minute. Okay, no, don't feel like that. Okay, it is also not the main point here. Okay, so you should look at this slowly and convince yourself that this is really bounded by that, and that all these steps are correct. But we will not expect you to whip out these type of arguments. So in other words, the examples that we will give you for sure on tests, on homework, we might ask you to do something that requires a little more time. But for the test, you will not have this kind of stuff that well, is a little puzzling how to come up with, right? The point is to understand the methodology and to relate it to recursive to recognize recursive objects like the factorial formula, and to be able therefore to find links between statements about these objects for some index to statements about the same objects at one index less. Okay, here's a different type of thing that you could prove by induction. It's not so easy to see like recursive things in here, at least they're not explicit, that for every positive integer, 5 to the power 2n, if I subtract 1 from this power of 5, I get an integer that is divisible by 12. Okay, this is a little puzzling. Why should that be? That if I look at the powers of 5, but actually only even powers, right? So 5 to the square, 5 to the 4th, 5 to the 6th, etc. If I subtract 1 from any of such power, I get some integer that is divisible by 12. Well, here's how you can read off such a. So it's convenient to note that if statement that 12 divides some integer, it's the same statement as that this integer is a multiple of 12. In other words, that there exists some integer j such that the integer in question is product of 12 and that integer j, right? These statements are all the same statement, really. So when you look at it in this light, then the statement really becomes this predicate that for any integer n, if I take 5 to the power 2n and subtract 1, then this thing is a product of 12 and some other integer. Okay. So again, so what does this? So now, what will the inductive step say? It will say that for any k, at least 1, if it is true that this power is divisible by 12, in other words, that this power minus 1 is a product of 12 and some integer j, then it is also the case that the product of 2 times 1 more integer in question, if I take this power and subtract 1, I also get a product of 12 and some integer. Okay. So I will assume in my statement, what can I assume? I can assume this thing, right? That 5 2k minus 1 is 12 times something. And it's this statement, because I just move 1 over here, and it is the statement that 5 to the 2k minus 1 is equal to 12 times something. Okay. So my predicate in the inductive hypothesis will look that way. And what I will have to be proving is a similar predicate about k plus 1, right? So namely that there exists some integer j prime such that, okay, so here is my hypothesis and what I'm going to claim based on that. So in the inductive step, for all k plus 1, I have to argue that if this predicate holds for k, then it holds for k plus 1. Now, what's the predicate? The predicate really was that this power 5 to the 2k is expressible as 12 times something plus 1. And under this assumption, I want to prove that 5 to the power of 2k plus 1 is also equal to 12 times something, but that could be something different, right? Plus 1. This is a statement that 5 to the 2k minus 1 is divisible by 12, and this is a statement that 5 to the 2k plus 1 minus 1 is divisible by 12. Okay, so let me solve that one on the board as well. Okay, so here we have this statement in question, right? That the predicate says 12 divides this expression, and we have argued that this is the same. Okay, this predicate is the same to saying there exists an integer j such that 5 to the 2n can be expressed as j as 12 times j plus 1. So this is the equivalent statement, and this is the one you will see that will be convenient for us to argue. So The theorem says that this predicate holds for all positive integers. And now let's do this proof by induction. So base step. This is to show that is P1 true? Right? And what does P1 say? P1 says that there exists an integer j such that 5 to 2n for n equal 1, so 5 to 2 is equal to 12j plus 1. Is it true? Is this statement true? Well, yes, because 5 squared is 25, and 25 can be expressed as 12 times 2 plus 1. So this statement is true for j equal 2. Therefore, there does indeed exist an integer that makes the statement true, right? And let's check. So what is this for n equal 1? What is this? This is 5 to 2 minus 1. So this is 24, right? And indeed, 12 to 5 is 24. Okay. What is the inductive step? The inductive step has to show that for every k at least 1, if pk is true, then so is p of k plus 1. Okay, that's our goal. Let's envelop this in terms of this predicate. So in other words, what we have to show is that for all k greater or equal to 1, if there exists a j such that, what is pk? It's this. It's this statement, right, for k, for n equal k. So there exists some j such that 5 to 2k is 12j plus 1. And we want to show then that an implication, if then. And now what is the statement pk plus 1? Well, it's a statement that there is some integer, but I could use the same variable, but it's going to be very annoying and hard to read. So I will use a different variable. Okay, although the quantification here applies here, and the quantification here will apply here. So these variables don't really clash, but to any human, it is much easier to read if I use different variables here. So there exists j prime such that 5 to the power 2, and what is my n now? The n is k plus 1, right? So I have to read off this predicate. This is the Pn. For n equal k plus 1, so it is 5 to 2 k plus 1. And this is supposed to be equal to 12 times j prime plus 1, right? This is pk, and this here is pk plus 1, right? Okay, so let's go and try to prove this implication, right? So, okay, as before, I will, okay, so I have to prove this, but I can use this fact. Which side is easier to relate? The right-hand side or the left-hand side? Well, the right-hand side is really a funny thing because it's that there exists some integer which matches this, and there exists some integer that matches that. These are closed formulas that are easy to relate to each other. So let's do the same. Let's try that. Let's again start from the left-hand side of what we have to prove. And let's try to relate it to the left-hand side of what we already knew. Well, what is this? This is the same as 5 to the 2k plus 2. Right? So this is the 2k plus 2, but it's just the rewrite. Now, when you have powers of some, Okay, when you take a base and you take it to a power, which is a sum of two powers, how do you, what's the rule for evaluating this? It's the power to the first element multiplied by the power to the second one, right? So this is just true about powers. Now we can note, I mean, the point of these rewrites was to rewrite the left-hand side of the target expression as some function involving the left-hand side of the previous one, of pk, so that I can kick in my inductive hypothesis, right? So I can say that there exists some j such that this expression is equal to 12j plus 1 times 5 to the 2, right? So right here, I used inductive hypothesis, right? This one. I need this, there exists, right? Because otherwise the statement doesn't make sense. What is the j here? No, what I'm saying here is that there exists a j which such that this expression is equal to that expression. And that follows from the inductive hypothesis, which says that there exists a j that allows me to rewrite this power of 5 with 12j plus 1. Okay, because that was the assumption that this power minus 1 is a product of, is a multiple of 12. Okay, so so again, what happened here, right, was that basically use sort of recursive relation on powers, right? That's what allowed me to relate the left-hand side here to the left-hand side here. Okay, and now the rest is again arithmetics, right? So I know that this thing is that there exists some integer such that this thing is equal to that. What I want is to be able to rewrite this in that form for some j prime, right? Because that's my target, that this guy is equal to such an expression for some integer j prime. So let's try to modify this so that to see this as a product of 12 times something plus 1. Well, how can we do this? So we have 12 times something already, plus 1 times 25, right? So I'm just okay. So let's cross multiply and see what happens. So this is 12j times 25 plus 1 times 25, right? I just multiplied this by both this part and this part of the summation. So can I see it as 12 times something plus 1? Yes, because it's 12 times 25j. So this part is definitely 12 times something. And now I want to see this one as such. Well, I can, because 25 is 12 times 2 plus 1, right? So this is that, right? And now I'm home because I can rewrite it as 12 times what? 25j plus 2. I take 25j from here and 2 from here, right? Plus 1. So this is my j prime. So in other words, there exists j prime such that this is equal to 12 times j prime plus 1. That was my goal, and it is shown, right? It is less perhaps clear, you know, how did I guess this, right? So how did we note that powers of these powers of 5, you know, have this pattern, basically, right? That they are always related to some multiple of 12 plus 1. But sort of, you know, creating this stuff is sometimes not so hard, sometimes hard. But proving it, and in fact, you can basically do it by seeing whether it's what kind of relations can be proved by this type of induction, right? If you knew that there is something holds about some lower powers of 5, you know, could you show that this also holds about the higher ones? Is there a relation between these? Okay. Okay. Let speak up if you have questions about this proof. And in the meantime, I'll try to go back to my slides. Okay, so that was my okay. Here's the last or the one before last example. I'm back to, I want to go back to the objects which are explicitly recursively defined. Okay, and powers of 5 were recursively defined. Okay, 5 to whatever power n is 5 to the previous power times 5. Here is your recursive definition, which you used actually here, right? So you used it in this proof. Okay, but you jumped a step. So 5 to the even power is 5 to the previous even power times 5 times 5. All right. Let's look at the explicitly recursive objects like sequences that are defined using recurrence relations. So here is a sequence. Its first G0 is -3. That's the base case of the sequence. And then you have a recurrence relation. For all integers greater or equal to 1, nth element in sequence is twice the previous one plus n square. Okay? So without the n square, this would be a geometric sequence. You start from some point -3, and every next point is twice the previous. Without this recurrence relation, this sequence would just be the sequence of squares, of integer squares, right? And because of this formula, it's somehow a mix. It's recursive, geometric, but with a offshot, with like a shift, quadratic shift. Here's what we claim, that the closed form expression for the same sequence, for any n equal to from 0 on, right? So it's the same sequence at all its points. The closed formula is 3 times 2 to the n minus this quadratic expression. So you know that this formula contains some geometric. If we didn't have this part, it would be a geometric sequence. It would have this term. Gn would be some initial value times consecutive powers of 2. In fact, we will have this power with a minus sign, right? Because without this, that would be, I would have a minus here, and all of this would be gone. And somehow, because of this, I actually went from the negative to positive, but I just have this funny shift. It's not easy to see that this is true or not, or like it's not easy to come up with these formulas, seeing the recursive relation. Okay, it's quite a jump from here to here. But let's first see whether, if you determine that these are the parameters, and you just wanted to test whether the parameters you found that expresses as a closed form are true. How do you do that? Using recursion. So here I have it. on my board. So again, Gn is a recursive sequence defined recursively using a base case and a recursive rule, right? Recurrence rule. And here is the closed formula I claim is correct. So proof by induction base case is n equal n equal 0. Okay, and this is a predicate. It's Pn, right? The Pn says that this sequence defined recursively has this closed formula. Okay, so let's see what this predicate says for n equals 0. It says P0 says that G0 is equal to this formula for n equals 0. So this is 3, 2 to the 0, minus 0 square, minus 4, 0, minus 6. So these are zeros, right? And the 2 to the 0 is 1. So this is 3 minus 6. So this is minus 3. And yes, correct. So this closed formula works for at the first point, does express this point correctly. Inductive step. What we have to show that for every integer at least 0, the predicate at k implies the predicate holding at k plus 1. For the case of the predicate, what is it? It is that, in other words, in this case, we are proving that for every k greater or equal to 0, if gk, I'm reading off this predicate, instantiating for n equal k. So let's do that. Gk is equal to 3, 2 to the k, minus k squared, minus 4k, minus 6. If this is true, then let's read off the predicate for n instantiated with k plus 1. It says that gk plus 1 is equal to 3, 2 to the power k plus 1 minus k plus 1 square minus 4 k plus 1 minus 6. And this is pk plus 1, and this is pk plus 1. Sorry, this is pk, and this is pk plus 1. Okay, so actually all my proofs today will use the same methods. My goal is to prove this, and I can use this in my proof. It is now, I do have an explicit recursive relation between this object and this object. So let's go and use it. I want to express gk plus 1 as this. Let's first express gk plus 1 as some function of gk, so that I can kick in this formula, and hopefully it will help me. So gk plus 1 is recursively defined as 2 times gk, right? So now I'm instantiating this, instantiate the recursive rule for Gn. For what index n? For n equal to k plus 1, right? That's what I'm doing now. So this is k plus 1, so this is k, and n is k plus 1, so this is k plus 1 square. And this supposed to work for n greater or equal to 1. Well, I'm claiming it's for k greater or equal to 0. There is perhaps some mismatch, but not really, because if k is greater or equal to 0, then k plus 1 is obviously greater or equal to 1. So therefore, this is indeed greater or equal to 1, and therefore I can use this formula. This might sound like battery, but the border conditions really matter, right? As anybody who ever tried to program some recursive algorithm, the base case, some missed base case is completely messes you up. Okay, so this is okay, right? But rewrite by this rule. So now let's use the inductive hypothesis. Use the inductive hypotheses. So namely this statement, right? To now see that GK can be rewritten by this formula. So let's do that. This is 2 times whatever GK was, and I'm supposed to be able to claim, to be able to use that GK is equal to the following expression. Sorry, -6, right? And don't forget this term, k plus 1 square. Okay, and the rest again is arithmetics, right? So now I have to see, is this right-hand side really the same as this one? Well, let's try to abridge between them, right? So let's try to somehow get them close to each other. Well, first, let's have this term in here. Well, that's the easy part. This is 2 times, so I can multiply each of these terms in the summation by factor 2. So 2 times this is 3 times 2 to the 1 more power. So it's that. Minus 2k squared minus 8k minus 2 times 6, 12. And then I have this k squared thing. Okay, so that's k squared plus 2k plus 1. Right, so this part is from here. This part is multiplying 2 times those 2 times this, right? And this part is here. Okay, so that's great. I have 3 times 2 to the k plus first power, so I do have here, and I have some funny expression. Okay, let's try to simplify this because I have the same powers. So I have minus 2k squared plus k squared, so it's minus k squared. I have minus 8k plus 2k, so it's minus 6k. I have minus 12 plus 1, so it's minus 11. And you know what? Let's, instead of, so now observe that 3 2k plus 1 minus k plus 1 square minus 4k plus 1 minus 6, in other words, the right-hand side. So this is the, so I'm starting with the left-hand side of my target. And I'm going to end at the right-hand side of my target. But let's rewrite this because there is still some gap between these two expressions. So 3 to the k plus 1 is already here, so I'm happy about that. Let's do this one. So this is what? K squared, it's minus sign, k squared plus 1 is k squared, k plus 1 squared, right? So it's k squared minus 2k minus 1. That's this. Minus 4k plus 1, so it's minus 4k minus 4. That's this. And minus 6, right? Okay, and now let's simplify. So it's 2k plus 1. So it's minus k squared is alone. Minus 2k minus 4k is minus 6k. Minus 1 minus 4 minus 6 is minus 11. And I declare victory. These two things are equal. Right? So of course, yes, you can try to get from here to here directly, right? It's just that it's uncomfortable because in order, it's much easier to sort of start now at this point, jump to the right hand side and start evaluating these expressions and simplifying them, and you will then see that they wrap around to the same quadratic formula, that you have here. And so now you're done. Okay, let me, okay. So somebody says, do we have to write left-hand side, right-hand side? No, you don't have to write, but it just might be helpful. So speak up now. If you, I open up for questions. This is all I have, and ask me.
Yeah, a quick question about the homeworks and stuff. Are the homeworks graded yet? Because on Gradescope, I checked to see if there's anything like any marks or slashes made by like any signs of
No,
grading.
I don't think they're graded yet.
Okay.
No, so when they're graded, you get an email.
Okay. So do you know how long it'll be before they're graded so we could study and catch our mistakes?
You know what? Like I can check right now, like what percentage is graded, but that's not. I will do that after the lecture.
Okay.
Yeah. They were at 50% on Sunday. When I checked. Okay. Next question. But you do have the solutions, by the way, right?
I think so. So, but because since there's a lot of problems and there's a lot of questions and like matching the solutions one by one. Yeah.
Oh, by the way, you're not gonna get everything solved in the solution. So we choose a bunch of random problems and only evaluate those. So your feedback that you get is limited to a random subset. For everything else, you have to basically understand. I mean, yeah. So the detailed feedback is for a random subset of problems. So you very much you have to understand the solutions, and you have to go through the solutions, and you have to match the solutions with your solutions. Absolutely, you have to do that.
Okay.
So, Professor?
Yes.
Are homework graded based on the grading or based on the completeness?
Okay, so right. On this one, I think I said 40% for completeness and 60% for the random subset, but this is gonna vary.
Okay, thank you.
Yeah, something, no, yeah, but expect that kind of fraction. Okay. Is there some questions about the lecture? Some point in these proofs that you want me to go over? When will I post? So I always upload it on YouTube, and I will also post the sheets of paper, and of course the slides, right? But the slides actually they kind of say, okay, this is what we want to prove, and the proof is on a sheet of paper. So somebody says, when will it post? So I post when I'm done with this. So I'll post after the lecture, and then the YouTube takes, for some reason, an hour to upload. Okay, do you guys have any further questions?
So this is mainly just like playing with arithmetic, basically.
No.
Not really, but like in a way
yeah,
that you're trying to match.
Yeah, no. So there's three elements here. There's a recursive. These statements are really, you have to see that they are about recursively defined objects. They are about summations, about something that a statement on n can be somehow related to the statement of n minus 1. So you have to make that jump between whatever we are saying is being said about some index n to something said, the same thing said about the previous index. And what's the relation? That's number one. The second move is that now that you've done that, you can kick in the inductive assumption and try to now and use the fact that the previous element in the sequence, something is true about it, something that the inductive assumption allows you to claim. So take that in. And the rest is usually some arithmetic transformation. So that was the meta procedure on all the proofs that you have seen today.
Okay.
Okay, all right. So good. So read this inductive stuff. Try to do exercises on it. Homework is due in 3 hours, and we'll post the next one on this stuff, right? And you can, of course, read ahead for strong induction that is coming next on Thursday. So thank you very much, and see you all on Thursday. And go to discussions on Wednesday too. Bye, everyone.